And thank you all for joining. As I mentioned right before I hit the record button, I've emailed and I put in the chat the this presentation and my notes document. And so you don't have to worry about taking notes. And you can use that as a reference. And what I'm doing is I'm just building upon these 4 presentations. So I have part 1 included. I have, actually most of part 3 already done, and I'm already working on part 4. So for this presentation, you'll actually begin at slide 85. And for the notes page, you'll begin on page 56. So if you're looking for where I am, that's how we'll do it. So today we're going to last time we focused on research methods, really the basics of research. This time we're going to focus on statistical analyses, and we're going to use several different programs as examples, but I'm going to really focus on helping you understand the basics of the stats in the first place. We will use some examples actually in all of the different programs, in Excel, in Jamovi, in R, Python, and I do have SPSS loaded up. I've got the same data set for that. And next time, we'll do a little bit more in SQL as well, even doing like SQL select statements and really trying to put it all together. So that's the goal for tonight. So the objectives of this session is to learn statistical methods, including measures of central tendency and measures of dispersion. So for example, mean, standard deviation. Learn how to run a frequency table in R and Python. And all of these are in the notes. All of these are examples, again, so you can always go back, whichever program you've selected to use, you can go back and you can run it in any of those programs. Also learn how to run inferential statistics in R and Python, and learn how to run a graphical representation, both in R and Python. So we're going to start, we're going to use a data set. It's called the cardio data set, and we're actually going to see it in all of these different programs. So I'm going to go out of screen mode. I'm going to go in and just show you how it looks in all of these different environments. So this is the Excel version of the cardio. So you can see it's a real simple, there's about 70,000 records. But then it has age, gender, and you can see it's age in days of life. So we'll even convert that to years. Gender, 2 options here, height and weight in the metric system. These are obviously blood pressure readings. And then we have cholesterol, glucose, smoking, alcohol, activity, and then a cardio risk. We also have this loaded up in R, and I have it loaded into a data frame in R, and we'll be able to run some output. I also have it loaded into Python, and I'll show you, I don't have it in a data frame format, but I'll show you how we're going to use it in Python. There's also a program called Jamovi, and Jamovi it's a much more user-friendly. If you don't like literally writing code to do your analysis in R, Jamovi looks a lot like SPSS. So if you've used SPSS in the past and prefer that methodology, then you can actually use Jamovi. Jamovi is a free download. And then finally, for those of you that do have access to SPSS, again, we have all of these same data set in all of these different formats. We can actually compare and make sure we're getting the same result. And in most cases, we do get the same result. There are a couple of times when we don't, literally some rounding errors, but that's that. So before we can start running analysis, there's a couple of data management things to keep in mind. And we'll work through these. One is just uploading and downloading the data sets. And in R and Python, what's super important is that you establish the working directory. It's also important that you understand and know how to transform and calculate new variables if necessary. It's important to be able to clean and summarize your data, and then finally have a way to validate your data. And Excel is really a good first step in doing that. So again, I'm going to go out here, and we're just going to go in R. And remember, there's two versions of R. There's the R Studio. That's what we're going to be looking at here. But there's also just plain old R, which just has a console here. But we're going to primarily use R Studio. When we're in R Studio, there's really four different screens you're going to be looking at. So the upper left is where you're going to be writing your code. The lower left is where you're going to get your output, and then you'll get your environment, and you'll get your plots over here. But it's super important, first of all, to start out with is to set and get your active working directory so that you're working off of the right data set. So we're in this, it's on my computer, it's in my D drive, and a data and an R drive here. And then once you do that, then you can, and I'm just gonna copy and paste, but you can get ahead. And so this is the data set. It's just the first 5 rows coming up in R. And then we've got a couple of other data sets. And again, to go from the CSV file, you're going to create this data frame called, and I have another data set here, it's called HL data for my health literacy data. So you're going to read the CSV file. This file is in this directory here. This is all in the notes page, so don't worry about all this little tiny font. And then we'll get the head of this as well. So we click, go to the next line, and now we have our HL data set with my 5 elements of my health literacy model. Once you've done that, you can go back now and you can create output. You can create things like, we can do like a histogram here. And we're going to do a histogram of age years. So it's going to be this, this column right here. The way you do that is you would type in hist, and then in parentheses, the name of the data frame. So this is cardio, with the $sign, and then the variable behind it. So we do that, and it creates this histogram here. We can also create a histogram of the age years. See how it changed now. We have a new histogram. We can also go into things like count. So we want to know how many records are in this data set. We can see here, we have our 70,000 records in here. And you can even do things like you can plot the data. You want to see all the records in the data set. So again, these are just simply some basics. So just basics in R, and you can do largely similar things in Python, doing those things. So let's go back to the presentation. Remember, okay, so let's go back to R, and we just want to do so we can do a summary, and we can see all of the data in here. So let me make this a little bit bigger. And so it's always a good idea to go through these and really look at your descriptive statistics and make sure that you're getting the right data elements. So take a look, for example, at the blood pressure readings. Okay, so this AP high and low, that's the systolic and diastolic. And you can see here we have a max systolic and diastolic that's non-physiologic. It's not even possible to have a systolic blood pressure of 16,020 or a diastolic pressure of 11,000. So these are obviously data entry errors that you always want to be mindful of. I've calculated a body mass index, and there's a max BMI of 298. That's literally impossible. You can see that we have a median and a mean, okay, but there's obviously some outliers here that are problematic. Our age numbers look pretty good, 29 to 64.97. So obviously a non-Medicare population in this case. So those are some examples of some things you can do. And then we can, of course, go in and we can create things like a frequency table. And so we have and this is just simply the frequency table of our total data set for people with positive for cardio. So about half of the population has a cardiovascular disease and half of it does not. Okay, so again, just some basics in R of how you can get some basic output. All right, so let's move on. So now we have a data set. We're going to clean and scrub it, make sure it's working the way we want it to be working. So now we need to go back really to the questions we asked last time. So what is the research question? What is the null hypothesis? And remember the importance of the null hypothesis. If you think today is warm, or actually today is kind of a rainy day. So if I say today is a rainy day, I have to compare that to what is not rainy, okay? If I say it's a hot day, I have to know what not hot is. So that's by definition what the null hypothesis is. We also need to know the assumptions that need to be met and the descriptive statistics that need to be run. So I got to put this back into screen mode. This is a little test selector program that I've created for you to help you figure out, like, what tests do I need to run? So you always need to be thinking about the purpose of the study. Why am I doing this study? So am I trying to calculate rates, like an odds ratio or a relative risk, or do like a survival curve? Am I looking for deeper insights? So maybe that's a qualitative study. Or am I trying to test a hypothesis? So if it's calculating rates, you run your analysis. If you're going to do deeper insights, that suggests a qualitative approach. You're still going to need a research question, and you're going to need a methodology, whether it's grounded theory, phenomenology, ethnography, there's others, case studies, and other types of qualitative designs. If it's quantitative, you still need a research question. You're going to start with descriptive statistics, and you're going to start by testing your assumptions. If your assumptions are not met, then you may need to be forced to use non-parametric tests. The most common examples of non-parametric tests are the chi-square test, the Kruskal-Wallis test, and the Mann-Whitney U-test. There's others. There's the sign test and different ones. Those are the main ones. Okay, so now let's hope that your assumptions are met and you're ready to do some inferential statistics. So what do you need to know how to do the test? So the first question is, what are you trying to test for? Are you testing relationships or are you testing differences? What do you need to know then next is, how many variables do I have? If you have one variable and you're testing differences, then you're looking at a one sample t-test. You could also be using a histogram or a pie chart. If you have two variables, now you need to know about your dependent and independent variables. If you have two groups, if you have one dependent variable and one independent variable with two groups, then you're looking at either a paired sample t-test or an independent sample t-test. And you can be using a bar chart. What if you have more than two groups? Then you're going to be looking at a repeated measures analysis of variance, a one-way or an n-way, it could be more than one way, analysis of variance, or a box plot. Oh yeah, so if you have more than three variables, then you're looking at a two-way ANOVA. If you have two or more independent variables, you may be looking at an analysis of covariance. If you have two or more dependent variables, you're looking at a multiple ANOVA, which is called a MANOVA. And then finally, when we get into relationships testing, if your variables are quantitative, meaning that they have, remember their interval or ratio variables, then you're looking at a correlation, a linear regression, and you can be using a scatter plot. If your variables are nominal, then you are looking at a logistic regression. So I know this is a lot of information, but it's all here on one screen, and if you follow it and you answer those questions on the number of variables, the number of groups, and the types of variables in each group, it'll actually lead you to the right statistical tests to run. Let me pause there just for a moment. Are there any questions on this? I know there's probably multiple questions. Let me check in my chat area here just to be sure. And feel free, I know this is a lot of information, so feel free to ping me later if you have more specific questions. But these are really fundamental. If you're trying to get a paper published in a journal, it's super important that you're using the right statistical test. So let's go back now to the research questions. Okay, so the research question needs to be a clear and focused and concise question that guides your project. So it needs to be specific. It needs to be something that you can actually answer. It needs to be researchable. So you need to be able to put a methodology to it. It needs to be significant. There needs to be a reason for the research question. And it needs to be clear and unambiguous. If you're looking at things that are not clear and are ambiguous, then you might be looking at more of a qualitative approach. Once you have your research question, then you need to come up with your hypothesis, which is your testable statement about either the relationship or the difference. And remember, you always start with the null hypothesis. The null states that there's no relationship or no difference. The alternative is the opposite. So the alternative will look a lot like your research question. So what you're doing with a quantitative study is you're testing that research question. So in this example, does the vaccination program reduce the incidence of influenza? So the null hypothesis is that the vaccination program does not reduce the incidence of influenza. The alternative is that it does. Before you begin your statistical analysis, then the next step is to look for the types of assumptions that you need to be testing for. And without going into all of those different ones, the main ones are going to be things like independence, normality, and linearity. So you have with the Durbin-Watson test for independence. A box plot is actually a very nice way to look for outliers. If you're looking at normality or a normal distribution, you can be doing a histogram. There's a test called the Shapiro-Wilk test. You can also look at the skewness and kurtosis of your histogram. A scatter plot is a nice way to look at linearity. You should also be looking at the homogeneity of variance. There's a Levene's test for both the t-test and the ANOVA, testing for homogeneity. There's also multicollinearity, which means, as these variables are so tightly intercorrelated. So there's what's called a variance inflation factor, You can also just simply run multiple correlations and see how tightly correlated they are. You have homoscedasticity, and you can look at a scatter plot for that. Reliability is the Cronbach's alpha. A model fit, if you're doing a logistic regression, is the Hosmer-Limashaw goodness of fit test. And then finally, sphericity is a test for equality of variances in regression. And there's the Mockley's test for sphericity. Of course, you have descriptive statistics, measures of central tendency, and measures of dispersion. So I showed you an example with the cardio summary and doing things like the mean age. In R, remember to always put that $sign between the data frame and the variable to get the specific variable that you're looking for. You can also be doing frequency tables. I showed you an example already, but you're looking at for counts and rates. It's a very good way to look for bias. You know, do you have equal numbers by gender, by race, by other factors that could be introducing bias into your sample. So really, how representative is your sample? So in your notes page, you can run a frequency table, and you can also convert that frequency table into a data frame and print that data frame. All right, so let's get into some of these statistical tests. So we're going to be looking at tests of difference and tests of relationships. We'll also look at some non-parametric tests, and then following this, we're going to look at some graphical representations. So the first one is the one sample t-test. So in this case, you have a sample, and you're comparing it to either a hypothesized or a population mean. So if Dr. Ali wants to test for whether the average blood pressure of the patients in his practice are different than the national mean for blood pressure, he could actually use a one sample t-test. So he might have a random sample of, say, 50 patients in the community, and he can run that test and compare it to a hypothesized national average, or actually go into a study and look for it. So what do you need to run a t-test? In a one sample t-test, you need one continuous variable. You need to have a normal distribution, and to test the assumption, you can use a histogram. So here's an example. This goes back to my commute time, but I have a mean, I have a standard deviation, and I have my 95% confidence intervals. So I have one variable, I have a normal distribution, and I'm looking at a histogram. So remember, one standard deviation represents about 2/3 of the sample. Two standard deviations represent your 95% confidence interval. So if you're beyond two standard deviations, your z-scores are going to show a statistical difference. So if my commute time, today is, 70 minutes, that's within the confidence interval. It's not statistically different than my average. But if tomorrow it's, 110 minutes because there was an accident on the road, then that is statistically different, and you can do that with a one sample t-test. Why are testing assumptions so important? Look at a couple of skewed distributions. This is a distribution of pets. It's not a normal distribution, so a one sample t-test would be problematic using that histogram. Another one that's skewed the other direction is distribution of age at death. It's not a bell-shaped curve. It's skewed. Here's the code. For time purposes, you'll just have to refer to the notes page. I've got all of these examples in the notes page, but I ran this in R. We've got a t-value of 2.5012 and a p-value of 0.03379. And I ran it in Python, and as luck would have it, I got the same result. So that's good. If you're getting different results in different programs, that can be problematic. But you go ahead and on your own, go ahead and plug those numbers in or put your own numbers in and see what kind of results you get. The next one is the independent samples t-test. It's still a t-test, but the difference here is you're comparing the means of two groups. Okay, so in the one sample, you had one group. Now you have two groups, and you have some way to determine the difference between those two groups. So in this group, we're going to be looking at smokers compared to non-smokers. And again, what do we need for the independent sample t-test? The dependent variable must be continuous. The independent variable must be categorical. So that's how you know if you're doing the right test. If your independent variable is not categorical, then you're going to have to do a different type of a test. For an independent sample t-test, it must have two levels. So yes, no, true, false, smoker, non-smoker. It cannot have more than two levels. If it has more than two levels, then you're going to have to move on to the analysis of variance. You need to have a normal distribution. You need to have homogeneity of variances. And the graphical representation can be a bar chart or a box plot. So again, in the lower example, in the upper example, these two groups are statistically different. There's no overlap. Okay, so there's no chance that just random chance that the variable could be wrongly classified. If you look at the lower example, the overlap is greater than the confidence intervals. And so in the lower case, there is no statistical difference. In the upper case, there is. Here's why homogeneity of variances are so important. Here's an example with my crude artistic skills, but in the bell-shaped curve on the left, it's a much tighter distribution than in the example. So if you're comparing these two groups, you need to know whether you have homogeneity, meaning the variances are the same, and if they're not, you may have to you can still use the test, but you have to look at it without the assumption of homogeneity of variances. Okay, so I ran my sample. I've got a p-value 0.0005, 4.316. Oh, and I should be mentioning the test statistic in a t-test is called the t-statistic. That might be super obvious, but it's important to kind of get your handle on. In the ANOVA, it's the F statistic. In the correlation, it's the R value. In logistic regression, it's the Wald statistic. So there's different names for these different tests. But again, we got the same result. That's a good thing. The next one is a paired samples t-test. So a paired sample t-test, you're going back to just simply one continuous variable, but you're looking at two different points of time. So we have participants in a 30 participants. They're going to be given a new drug to lower their cholesterol. And we're going to do a test and a retest, okay? And so you could use a paired samples t-test in that example. Okay, so what do you need for a paired sample t-test? Again, one continuous variable, only 2 points in time. If you have more than 2 points in time, then you're going to be using a repeated measures ANOVA, not a t-test. You need a normal distribution, homogeneity of variances, and you can do a bar chart or a line graph. Here's the test, here's the code in R and in Python, and we get an RT statistic, negative 163, so the same result in both programs. Moving on now to the one-way analysis of variance. The one-way ANOVA is just like the independent sample t-test, except that you have more than two groups. Because you have more than two groups, you're also going to have to do what's called post hoc testing. because all it's going to test for is whether there's a difference among the groups. It's not going to do the individual tests between the groups. That's why you need the post hoc tests. And no, you can't just simply do multiple t-tests on those groups. If you do that, you significantly increase your risk of a type 1 error. So in this example, we're looking at blood pressure readings in groups that do aerobic exercise, resistance training, and flexibility exercises. So the box plot is actually a really nice way to graphically look to see if there's a difference. And the way you interpret a box plot is you just look across, and obviously sedentary is significantly lower than those two. If you look at the difference between moderate and high, there's no statistical difference in that box plot. But clearly, if you look at sedentary versus high, there's a big difference. So what do you need for a one-way ANOVA? You need the dependent variable must be continuous. And again, the dependent is always that outcome variable. The independent variable has more than 2 levels. If it only has 2 levels, you can technically still run it, but you might as well have just simply run the independent sample t-test. You need that normal distribution. You need homogeneity of variances. You can do post hoc testing, and there's different post hoc tests based on that homogeneity of variance test. And the graphical representation is the box plot. So here's our one-way ANOVA in R and in Python, and roughly the F. So remember, in ANOVA, the statistical test is the F statistic. So in here we've got a 32.61, in Python 32.61. So we're getting the same results. A two-way factorial ANOVA, the difference here is now, instead of just simply 2 groups, you have 2 independent variables. Okay, so you still have one continuous dependent variable, but you can have more than one independent variable. And the independent variable can either be continuous or categorical. Okay, but it's for and it's what you're looking for. What are you trying to achieve with a two-way ANOVA? You're looking for what they call main effects and interactions. So up until this time, what we've been looking at are main effects. Was there an effect? Was there a difference? Or was there a relationship? With an interaction, what you're looking for is, did these 2 lines cross? Did one variable impact the other variable? And that can be a very interesting type of research to look at. So you can actually in all of these different statistical methods, you can test for main effects, but you should also test for interactions. Like I mentioned earlier, you can also do an ANOVA with repeated measures. Again, the difference here is if you're looking at more than 2 points in time. So in our example here, we're looking at diagnosis of depression, we're looking at cognitive behavioral therapy, interpersonal therapy, and pharmacological therapy. And we're looking at baseline 3 months, 6 months, and 12 months. So we can't do a paired sample t-test, but we can do a repeated measures ANOVA. So again, the dependent variable must be continuous. The independent variables are going to be at different points in time. You're going to test for main effects and interactions. You're going to use post hoc testing, and you're going to test for the assumption of sphericity in this example. The next one is called the analysis of covariance. This is a very interesting test. It's actually combining the analysis of variance with regression, with linear regression. And so what you can do here is you can basically look at the impact of a third variable on your dependent variable. So for example, we have two groups here, and we're going to put them into a weight loss program. So the dependent variable is the weight loss. You have a treatment and a control, but you have a covariate here. The covariate is their initial body weight. And so what you're going to have is basically a reclassified difference based on that. So maybe the people in the treatment group were significantly heavier than the people in the control group. That would be a violation of an assumption, number one. But you can also use that to do it's actually looking at that third variable and the impact that that third variable has on the relationship between the other two. So you can do ANCOVAs in R and in Python. These results are in the example. And then the last ANOVA is called the MANOVA, the multiple analysis of variance. And the significance here is that you have more than one dependent variable. So in all of these other cases, you had one dependent variable and either one or more than one independent variables. In the case of the MANOVA, you can actually have more than one dependent variable. They do this a lot in financial types of studies, but in this example here, we're looking at different types of fitness scores, looking at cardiovascular fitness, multiple muscular strength, and flexibility. So 3 different dependent variables. All right, I'm going to take a breath here. We're going to move now from testing differences to testing relationships. Let me pause. Any questions, comments? I know it's hard because it's a information dump, but if you do have any questions, feel free to put them in the chat. All right, we're going to move on to correlation. So correlation and regression are similar, but not exactly the same. The correlation, it does not distinguish between a dependent and an independent variable. You're simply looking at the relationship between 2 variables. So, and you're just simply looking at that, literally that correlation coefficient. So in this example, we have but the correlation does imply that both of the variables are continuous variables. They're not categorical variables. So in here, we're looking at physical activity level and a cardiovascular fitness score. So again, let's look at some of the requirements. You have 2 continuous variables. Your assumptions here are linearity, homoscedasticity, and you're looking at a scatter plot. So here's an example of homoscedasticity, meaning the variance is about the same through the range of scores. In some cases, you may have what's called heteroscedasticity, which means the variance is changing. You can see that as you move to the right on your line of best fit, the variation increases. So that's what we call heteroscedasticity. It's easy to run a correlation in both R and Python. I put the code in here. I actually used the sample data set. So we're creating a correlation. Here I'm literally doing the correlation between the systolic and the diastolic. It's an easy one here. But I put both the R and the Python output on the same screen. So you can see the correlation coefficient is 0.016. Next is linear regression. So the difference between a correlation coefficient and linear regression is now you are identifying a dependent and an independent variable. Okay, so but in linear regression, you're still implying that both of these are continuous variables. So in this example, we can do a linear regression between systolic or diastolic pressure and the body mass index. and the purpose is to determine the relationship with these two variables. So why are you trying to do that? You're actually trying to solve the equation y equals a plus bx. So y is the literally the y the y is the dependent variable. A is the y-intercept, so it's the all the way to the left here. This is literally that y-intercept. B is the independent variable, and x is the slope of the line. And this this could be a positive number. It also could be a negative number. But what you're trying to do here is, if you know b, or if you know x, can you predict y? And so that's the whole purpose here. So and that's why linearity is super important here. If you don't have a linear relationship, then you're going to have to use some other methods to get a more accurate regression line. So again, it's easy to run linear regression in R. And in Python, you get a lot of data, a lot of results. Luckily, in Python, it actually produced a table, which is much more readable than the R output. But in either case, you just have to get comfortable looking at your output. All right, you can also have multiple linear regression. And what that means is that you have still one dependent variable, but you can have multiple independent variables. And in multiple linear regression, you can actually have a combination of continuous and categorical variables that build your model. And what you're trying to do is you're trying to predict. So you're trying to predict the variable. So a lot of equations come out of either like a risk score, like a cardiovascular risk, or our new prevent calculator. Those are all using either linear regression or logistic regression, or in some cases a combination of the two. So again, it's just a variation on the formula, the y equals a plus bx. It's just noting it differently, but basically you have one y-intercept, and then you're adding the y-intercept plus the slope plus all of your variables to get to go from a simple linear regression to a multiple linear regression. Logistic regression, the main difference here is that your dependent variable is categorical. It's not continuous. So this is if you're looking at like mortality, alive or dead, if you're looking at readmitted, yes or no, that's how you'll use a logistic regression. So again, for outcome types of studies, had a heart attack, didn't have a heart attack, they're going to be using logistic regression as the tool. Okay, so how do they do that, and what does it look like? So it's called logistic regression because it's actually calculating the logic function, and that logic function is going between 0 and 1. Okay, so that's why when you set up your variables in logistic regression, they need to be coded as zeros and ones. If they're coded as something else, if it's ones and twos or yeses and nos, the program itself will actually convert it for you. But technically, it's doing the math and it's kind of crazy math. And you really wouldn't be able to do this kind of analysis by hand unless you had several months to play around with the numbers. And it's pretty amazing that you can run and get your output in literally a matter of seconds with this type of technique. But again, we have examples in R and in Python, and we're getting the same results. Again, remember in linear regression, we're looking at the R value. In logistic regression, we're looking at the Wald statistic. And again, because it's a categorical, you can also calculate an odds ratio. You're going to get a couple of other scores with this. You're going to get a pseudo R square. There's a couple of different ones. There's a Nagelkerke. There's a Cox and Snell. There's also a McFadden score. But those are similar, not exactly the same, but similar as the R square. I didn't mention that, and I probably should have. In linear regression, the R square is the measure of variance. And so the R square becomes a really important number. So if you have a correlation coefficient of 0.4, that means you have a R square. 0.4 times 0.4 is 0.2. So, and that's telling you that you're able to explain about 20% of the variance between the independent variable is explaining about 20% of the variance or the variation in that dependent variable. All right, now we're going to move on to the non-parametrics. So a very common test used in statistics is the chi-square test. There's actually two different versions of the chi-square test. There's the chi-square test of independence, and there's also the chi-square goodness of fit test. So chi-square is used many times when both your dependent and independent variables are categorical. So if they're both categorical, you can't do a t-test or an ANOVA. You can't, and if you're testing for differences, you can't run a regression test. But you can use a chi-square test. So here's the example of the output. But also always remember whether you're doing the test of independence or the goodness of fit. The first one was the test of independence. The second one is the goodness of fit test. Some other non-parametric tests that you should be aware of is the Mann-Whitney U-test. So here's an example where you have two independent samples. So what would be the parametric equivalent to the Mann-Whitney U-test? Anybody? The Mann-Whitney U-test is the non-parametric equivalent to the independent samples t-test. The Kruskal-Wallis, the one at the bottom, is a test of more than two independent samples. So the Kruskal-Wallis test is the non-parametric version of the analysis of variance, the one-way analysis of variance. There's other non-parametric tests. There's the Wilcoxon test. There's the sign test. There's other techniques, and you can do all of these in both R and in Python. You can do the Mann-Whitney, you can do the Kruskal-Wallis. Okay. Take a breath there. See if you have any additional questions. All right, the final thing is graphical representations. So the graphs are really important, especially in figuring out how to represent your data, in a manuscript or in a report. So one of the most common ones is the histogram. And again, the purpose of the histogram is to really determine whether you have a normal distribution. And you're never going to see a perfectly shaped histogram, but it is important to look for these and to see, maybe you need to be looking at the median instead of the mean, for example, or whether you need to be actually move into a non-parametric test because it's too much of a skewed distribution. A bar chart can be a good way to compare groups. So in this example, we have, we're looking at workplace stress compared to levels of physical activity. And I have the the 95% confidence interval, so you can actually eyeball this kind of like the box plot and see that there's a difference between sedentary and high, but definitely not between moderate and high. You can also do a line chart or a line graph, and these are good, especially for the paired sample test or the ANOVA with repeated measures. So if you're looking at things over time, for example, this can be a good way to do it. If you're looking at test scores, pre-test, midterms, and finals, that would be a good example here. A pie chart is popular. It's probably one of the least informative tests. You could frankly use a frequency table and get the exact same information. But a pie chart is something that is used, and it can classify groups. But it can be used as a good visual representation in a report or in a manuscript. A scatter plot is really good for looking at your correlations or your simple linear regression, looking at the distribution. And what you're looking for is, can you actually visualize that line of best fit? If you're creative and you look at this, you can kind of almost imagine where that line of best fit would kind of be going through here. So you can see a correlation here. But you can also see that there's a fair amount of variation. If you can't really see that line of best fit, that really means that you have a pretty low level of correlation. And like we shared, the box plot is a good way to visually represent differences in things like for example, a one-way ANOVA would be an example there. Okay, so again, it's important to, we talked about these already, but going back to always making sure that you're testing, identifying those assumptions and testing for those assumptions. Sometimes, you have to do the study. So sometimes increasing your sample size will help. But in other cases, it's not going to help you, and you may have to look at other techniques like a non-parametric test. There's also, and just in final summary, there's also newer, more AI methodologies. One of them that I've been looking at, and we're going to dig deeper into these next time in part 3. But doing things like a random forest analysis. And let me go out of here. Let me go back into Python. And let me just give you one example. I did find an example where we could do a random forest. I can find it here. I may have to open it up. It may be in my document. Bear with me here. This is my trusty Word document. I wanted to show you, because sometimes when we think of these AI analytics, it's like it doesn't seem possible to even be able to do these. But there are some examples where we can actually do these. Let me see if I can. I should have had it all queued up for you ahead of time. Is this my? Yep, here's my random forest. So let's see if I can get this to work. Oh, this is the R example. Yeah, so let's run this in R. And with these, it takes a moment. Oops. Need to. There we go. Okay. So in both, you can see here in both R and Python, what's necessary in many cases is to actually load the libraries that you need to run the test. So we're going to select all of these. I already have them loaded in here. And all you do in R is you just simply hit the run button. And again, this is a lot of math. It's a lot of computing power. And here's our example here. So we'll go over what this all means more on the next time. But let's see. Here's our output. And now we're going to, and just to show you in the Word document, I created these tables so you can see this is the R version. And this is the Python version. Oops. I don't know if that's going to work. So it's running. It'll take a moment to get our output. So you can play, I have these examples in the document, so you can kind of play around with them yourself. And it's a lot of computing power, especially since we're also on a Zoom here. So, but the output will look like this. It looks kind of crazy. A random forest is basically, think of it as a multiple regression analysis. So with that, let me go ahead and stop sharing. And I have time built in here if you have any questions here, but I also wanted to not just ramble for the whole time, but give you a chance to reflect.
There was some questions in the chat, Dr. Dunn.
Hi, Pat.
Okay, and I think I'm going to go ahead and stop the recording.